through those column ones or last columns within the gels that we run. So we call these a ladder, or sometimes they're called a DNA standard. So here you can see in well number 1, we loaded the ladder and it had a band at 5, 4, 3, 2, 1.5, 1 and 0.5. Now, considering their point, that to me automatically says that they are kilobase pairs, which means 1,000 DNA base pairs. If it was 5,000, 4,000, 3,000, 2,000, I would say that that is most likely to be base pairs instead. So usually we load them in the first or the last well. Sometimes we load them in both the first and the last well. And they contain, this is what is important to know a definition of a ladder or a standard. They contain DNA fragments of known lengths. So we know how many fragments there are and we know how long each fragment is. Now what that allows for is that allows us to actually determine the unknown fragments. So number 2 here is my unknown, but I know now that this one is going to be 5 kilobase pairs. I know that this one is going to be 2 kilobase pairs. I know that this one is going to be 0.5 kilobase pairs. And it's just about this one here. So this one here, you can see that it's a little bit closer to the 2 than it is to the 3 when I compare them. So I reckon it's probably around 2.3 kilobase pairs. And then so long as it's a reasonable estimate and you are close enough within your guess, that's good. Yeah, so you can use the ladder to determine the unknown lengths. Now, you have to run a fresh ladder every time you run a gel. You can't use the same ladder for one gel as another. And I want you to think about why. So just give it a pause, think about why. All right, so there's not a gap for this, but I do want you to annotate some reasons. So why must we do this? Every time you have a slightly different gel viscosity. So remember back when we talked about the factors that affect gel electrophoresis, one of them is the gel viscosity. So if you run one gel versus another gel, one of them might be a bit thicker. If it is a bit thicker or a bit more viscous, it's going to run slower. So you always have to run a fresh ladder with every gel. In addition to that, you might also get slightly different voltages. Yeah, and if you get slightly different voltages, that again, the higher the voltage, the further it's going to move through. So you have to put a fresh ladder in every time. The last thing that you might get that's slightly different is you might have slightly different times to run the gel. So if you have a bit longer in one running, then you might end up with it moving further along. So every single time you load a new sample, if you want it, you must load your ladder. You cannot use a ladder from one gel to measure against another gel. So here, for example, I want you to pause and try and label on your one. You can do it in pencil, whatever you want. Try and label how long you think each one of these fragments is, and then we'll work through it together. I'm hoping that you've paused and you come back and you're like, oh, I know exactly what the answers are and I'm just going to tick them off as we go. So let's have a look at sample A. Sample A has one band. It matches here with my 1,000 base pairs. So I would say that that one is going to be 1,000 base pairs. In sample B, we can see that it's got one band here. It's going to be at 800 base pairs. And another band here, it's going to be at 200 base pairs. Sample C has got a band here at 600 BP, a band at 300 BP, and a band at 100 BP. Now, do you notice anything about these three samples? I'm hoping that you've come up with the fact that every well adds up to 1,000 base pairs. Now, what you think about this in terms of bacterial transformation or in terms of lengths of DNA. To me, this first one here in sample A, that just has one length of DNA. Yep, that's 1,000 base pairs long. In the second sample, they add up to 1,000, but what you're actually looking at is a length that's 800. Ooh. Sorry, guys. A length that's 800. Let's just clear that off. And a length that's 200. How could we have gotten that 1,000 base pairs to be that? To me, this indicates that it was cut by a restriction enzyme. And it was cut once by that restriction enzyme to make 2 fragments. The last one here has got a section of DNA that's 600, a section that's 300 base pairs, and a section that's 100 base pairs. So in order to do that, I say it must have been cut 2 times by a restriction enzyme. Let's just have another look because this one's a little bit more what you might see. So here's your ladder going down in well number 5 this time. You see that we've got a band that's a bit, all of these bands don't quite match up with my ladder, but they're in between this one and this one in value. I reckon this one's going to be about 4 kilobase pairs. I reckon this one's going to be about 3.6. I reckon this one will be 2.4 and this one will be about 2.6. Yeah, so long as you're making reasonable attempts, that's good. These guys here are pretty close to 6.56, so I'm going to call them 6.5. And then I've got this one in between them as well. And that's between 6.5 and 4.3. Let's just give it a 5 kilobases. So the better your ladder is, the easier it is to determine the lengths of the unknowns. And that is the end of just looking at some general bits. The next bit that's really important to go through are some questions, because it's all good and well to know all of this theory, but now we've got to put it together and start answering questions.